Roman engineers discovered a chemical reaction 2,000 years ago that released enormous heat. They used it to build the Pantheon. Today, a startup is using its same reaction to store renewable energy as heat on demand at industrial scale. This is cement-based thermal energy storage. And it might be one of the most overlooked technologies in the clean energy transition. Electricity and heat are the two common forms of energy we use in life. Wind turbines and solar panels generate electricity. We have batteries, grids, and wires to store and move it. But heat is different. You cannot push heat through a power line. And a huge portion of what humans actually need is heat, not electricity. That gap is the problem this video is about. 30% of all global energy demand is heat, not electricity. Heat. 20% goes to industrial processes, making steel, processing food, manufacturing chemicals. 10% heats homes and water. Almost all of it still comes from burning fossil fuels. Solar panels and wind turbines generate electricity. They cannot produce the continuous, high-temperature heat that industry requires. That's the gap. A battery is any system that stores energy and releases it later. The phone battery in your pocket stores electrical energy in chemical form. When you need it, it flows as electricity. A thermal battery does the same thing, but stores energy as heat instead. Charge it up when electricity is cheap. Release heat when it's needed. Same principle. Different output. And for industries that need heat, that distinction matters enormously. Roman builders mixed quicklime, calcium oxide, with water to make concrete. The reaction released significant heat. Roman engineers used that heat to cure concrete faster, enabling larger structures. What engineers discovered much later, the reaction runs in reverse. Apply heat to calcium hydroxide and it releases the water, reverting to calcium oxide. The energy put in is recoverable. That reversibility makes it a battery. Store energy by driving the reaction one way. Recover it by driving it back. The reaction, calcium oxide plus water, gives calcium hydroxide, releasing heat up to 538 degrees Celsius. Run it in reverse, apply heat to calcium hydroxide, and you recover calcium oxide in water. Charging, electricity drives the reverse reaction, dehydrating the material back to calcium oxide. Discharging, add water to calcium oxide, release heat on demand. The critical property, energy is stored in chemical bonds, not as temperature. There are no thermal losses during storage. Pellets can sit for weeks without degrading. The chemistry was understood by the 1970s. Two problems blocked commercialization. First, the goop problem. At scale, hydrating quicklime produces an unmanageable expanding paste. Not a stable solid you can engineer around. Cache Energy solved this by forming the cement into small pellets about the size of a corn kernel, bound with a proprietary additive that maintains structural integrity through repeated thermal cycling. Second, electricity cost. Storing heat from electricity only works economically when electricity is cheap. Wind and solar have now made cheap electricity available for hours every day. That unlocked the economics. Cache Energy is a small startup based in Champaign, Illinois, about 10 people. They have two reactor models. The small unit is roughly 15 inches in diameter and 8 feet tall, producing 100 kilowatts of heat. The large model produces 1 megawatt. Storage uses standard grain silos, the same infrastructure found on farms across the U.S. One silo holds charged pellets. One holds discharged pellets. The reactor itself has no moving parts. Cost target, well below $25 per kilowatt-hour of storage capacity. Lithium-ion grid batteries run around $150 per kilowatt-hour. That cost gap is enormous. 5 steps. 1. Surplus wind or solar electricity is available, cheap or nearly free. 2. That electricity heats a reactor, driving water out of calcium hydroxide pellets, converting them to calcium oxide. 3. The dry pellets move to a storage silo at room temperature. No insulation required. No energy bleeds away. 4. When heat is needed, pellets feed into the discharge reactor. Water is added. The reaction releases heat up to 538 degrees Celsius. 5. That heat transfers to a factory process, a building, or a campus heating system. The silo is the key insight. Energy stored in chemical bonds does not leak. Cost is what determines whether a technology actually gets deployed. Lithium-ion grid storage costs around $180 per kilowatt-hour. That's fine for electricity storage. But it's far too expensive for delivering heat at industrial scale. Pumped hydro, pushing water uphill and releasing it through turbines, runs around $60. Molten salt thermal storage, used at some solar plants, around $30. Cement-based thermal storage targets below $25 per kilowatt-hour. The materials are abundant and cheap. The infrastructure is grain silos and a simple reactor. That cost gap is why this matters. Cache Energy's first major test is at Whirlpool's KitchenAid manufacturing facility in Findlay, Ohio. This is a real industrial plant with continuous heat requirements, not a controlled laboratory setting. Whirlpool has reported performance exceeding expectations. Why start with industry? Factories need heat continuously. They cannot simply switch to solar panels. And natural gas prices are volatile. A predictable, low-cost alternative has real financial value. This pilot demonstrates that the technology works under real industrial conditions. University of Minnesota Morris has 2 large wind turbines, but a heating problem that electricity alone cannot solve. Heating 38 buildings through Minnesota winters requires 4 times more energy than total campus electricity demand. That heat comes from natural gas. Meanwhile, on windy days the turbines produce surplus power that the campus sells to the grid at minimal value. Cache Energy delivered a thermal storage system in early 2026. The pilot is currently heating a single building, with plans to scale to the full campus. The university's sustainability director reports the system is performing well. Renewable energy has a timing problem. Solar panels generate the most electricity at midday. But electricity demand peaks around 6 p.m., when people return home. Wind generates most at night, when demand is low. The result, surplus renewable electricity at the wrong times. In some regions of the U.S., wholesale electricity prices actually go negative during peak solar hours. Generators pay the grid to take power. Thermal storage solves this directly. Charge during the surplus. Discharges heat whenever it's needed. The timing mismatch becomes an advantage. Cheap electricity becomes stored heat. 4 questions remain unanswered. First, pellet durability. Hundreds of charge-discharge cycles over years of real operation. Nobody has published long-term data yet. The binder chemistry is proprietary. Second, round-trip efficiency. The ratio of heat output to electricity input has not been publicly disclosed by Cache Energy. This number matters for economic comparisons. Third, scale up. Moving from a 10-person startup running pilots to mass production is a significant engineering and manufacturing challenge. Fourth, competition. Hot rock thermal storage, molten salt, and other thermochemical pairs are all targeting the same industrial heat market. Which approach wins for which application is not yet clear. Industrial heat generates roughly 6 gigatons of CO2 per year. Residential and commercial heating adds another 3. Together, 9 gigatons of CO2 annually from heat alone. That exceeds emissions from all transport, every car, truck, ship, and plane combined. And yet heat is almost absent from mainstream clean energy discussions. Replacing combustion-based heat with thermal storage charged by renewable electricity eliminates those emissions directly. The feedstock is calcium oxide from limestone, one of the most abundant materials on Earth. No lithium, no cobalt, no rare earths. 3 futures if the technology proves out at scale. First, industrial decarbonization. Steel mills, cement plants, food processors, these industries have almost no practical clean alternative for continuous high-temperature heat. Thermal storage is one of the few approaches that can actually work. Second, home heating. Cash Energy's founder describes a home-scale unit beside a water heater, charging on cheap overnight electricity and supplying daytime heat. That would eliminate gas furnaces. Third, grid balancing. Every unit of surplus renewable electricity absorbed by thermal storage reduces curtailment and makes renewable energy projects more economically viable. And calcium oxide is just the first chemistry. Researchers are characterizing dozens of other thermochemical pairs with different temperature ranges and energy densities. 5 things to remember. 1. 30% of global energy demand is heat. Almost all of it still comes from burning fossil fuels. This is the biggest clean energy problem most people have never heard of. 2. The chemistry is 2,000 years old. Calcium oxide plus water gives calcium hydroxide plus heat. The reaction is reversible. That reversibility makes it a battery. 3. Cash Energy solved the goop problem with corn-kernel-sized pellets held in grain silos. The reactor has no moving parts. 4. Real pilots are running now. Whirlpool's KitchenAid factory in Ohio. University of Minnesota Morris campus. 5. If it scales, clean industrial heat, home heating without natural gas, and better economics for renewable energy. Subscribe for more breakdowns of science and technology topics. Leave a comment. What question do you still have about thermal energy storage?